Okay, so we've talked about discrete random variables, given some examples. What we're going to talk about now is expected value, variance, and standard deviation of a discrete random variable. You remember back at the beginning of the course, we did the mean, the variance, and standard deviation of data, and essentially this is the equivalent in the probability case. Expected value of a variable is a synonym for the mean of that variable. So we're going to go back to one of the problems that we looked at, which was the number of cells. As far as our table was concerned, we had x and p of x. We may have had y there. And the values were 0, 2, and 4. The probabilities were 0.109, 0.162, and 0.729. So in giving you an idea about the expected value or the mean in this case, one thing you need to know right off the bat, we are not using the same formula that we used in the case of data. The ideas are analogous, but if you use the formulas that we used in the data portion of the course, you're going to get wrong answers. So graphically, we can look at this by using something called a needle diagram. I recognize the origin is supposed to be at 0 here on the x-axis, but for the purpose of seeing this, I'm actually going to move 0 over here so it's easier to read. There's 2, there's 4. On the vertical axis, what we're going to do is put probabilities. So the highest probability we've got is 0.729. So each one of these marks here, I'm going to make equal to a quarter. So there's 0.25, 0.5, and 0.75. And we'll get a rough sketch here. So this is little p of x. And what we're just simply going to do is draw a little needle, where the height of the needle, or the height of that line, it goes up to the corresponding probability. So at 0.109, that's about 2/5 of the way up to our first tick mark, so right about there. In the case of 2, 0.162, so that's going to be a little bit higher, maybe right about there. And then for 4, the probability is 0.729, so that's certainly going to be, no, that's not going to be a straight line, even though it should be. Let's try that again. We'll do a straight line. Oh boy, I just can't draw right now, but we'll take this up to right about there, which is about 0.729. So let me put these in here so that you know these heights. And in the process of calculating the mean from a physical standpoint, now what you want to do is start thinking of this almost as if it was a seesaw, or the possibility of working with a balance scale. And what we want to do is somewhere along here, put our little fulcrum. The needles weigh an amount corresponding to their probabilities, whether it's ounces, grams, whatever, they're standing there. The needles have to stay where they are, but we can move this. Where do we put this so that this will balance? Okay. That's that notion of the expected value. Another way of thinking about it, when we look at this, is that if we were to turn these into fractions, 0 is going to happen 109 out of every 1,000 times. 2 is going to happen 162 out of every 1,000 times. And 4 is going to happen 729 out of every 1,000 times. So basically, we can take a look at this from the standpoint that we're going to have, on average, out of every 1,000 times, we're going to have 109 zeros, 162 twos, and 729 fours. If we were to take the average of 109 zeros, 162 twos, and 729 fours, what we would end up getting is 3.24. We get this mathematically, expected value of x, by taking each value of x and multiplying it by its corresponding probability. So 0 times 0.109 plus 2 times 0.162 plus 4 times 0.729. That gives us our 3.24. And so generalizing here, the expected value or mean, capital E of x, is equal to the sum, x goes from negative infinity to positive infinity, of x times p of x, and just recognize that we're going to add up the products that are relevant to the random variable we've got. In some cases, especially when we get to the continuous case, we may be working with the entire real line, but in this case, we're really only working with 0, 2, and 4 because all of the other probabilities are, all the other values of x have probability 0, so we can just ignore them for the sake of the summation. So essentially, putting this triangle over here at about 3 1/4 would cause this thing to balance. And as you know from being on a seesaw, if you've got two people of different weights, the person who's heavier needs to be closer to the middle, and the person who's lighter needs to be farther away. And so that's the explanation of the physical meaning of it. Okay. Similarly, if we go back to the number of trials, the number of things we had to test when we looked back at problem 3.3. Our table here, we had x, 2, 3, 4, p of x equals 1/6, 1/3, and 1/2. So the expected value of x is going to be 2 times 1/6 plus 3 times 1/3 plus 4 times 1/2. So that gives us 1/3 plus 1 plus 2, or 10/3. Again, in interpreting this, it's impossible to test 3 1/3 of these items. So the way to think about this is if we had to go through this process over and over and over again, the average of all the 2s, the 3s, and the 4s, based upon their probabilities, would be between 3 and 4. At 3 and 4, it would be at 3 1/3. So we're a little bit closer to requiring 3 tests than we are to requiring 4 tests on average.